the Great Oxidation Event. The sky above early Earth isn't blue, it's orange. The oceans aren't blue either. They are green, then rust red, then the deep purple-black of chemistry boiling in darkness. The year is 2.4 billion BCE. The continents you know don't exist. The air is unbreathable. And somewhere in the shallow iron-rich seas covering what will one day become Ontario, Canada, something is alive, something invisible, something that is about to commit the single greatest act of mass murder in the history of this planet. Not with teeth, not with venom, not with fire, with breathing. This is the Great Oxidation Event, and the killers were cyanobacteria, microscopic, countless, completely indifferent to the world they were about to end. Before they arrived, Earth's atmosphere contained less than 0.1% oxygen. The dominant life forms were anaerobic archaea, organisms that had been thriving for over 1 billion years in a world of methane and iron chemistry, building complex metabolic systems perfectly calibrated to an atmosphere that would suffocate you in seconds. They were not primitive. They were not struggling. They were the rulers of an ancient world with rules that had held stable for longer than the human mind can genuinely comprehend. And then cyanobacteria invented photosynthesis, and their waste product, the exhaled breath of trillions of organisms doing nothing more than harvesting sunlight, was oxygen. To the anaerobic world, oxygen was not life, it was poison. Geochemist Heinrich Holland at Harvard formalized what we now call the Great Oxidation Event in 2002, after isotopic evidence in sulfur deposits confirmed a dramatic atmospheric shift. The evidence is locked in rock. Specifically, in banded iron formations found on every continent on Earth, layers of iron oxide deposited when dissolved iron in ancient oceans reacted with the new oxygen and sank to the seafloor. The oceans literally rusted. You can hold a piece of that rust in your hand today in the Pilbara Craton of Western Australia, and you are holding a record of the day the world's chemistry changed forever. The atmospheric methane that had kept early Earth warm was chemically destroyed by the new oxygen. Geochemist Lee Kump at Penn State estimated that methane concentrations dropped by a factor of roughly 1,000 in a geologically short window. The greenhouse heating system switched off. The planet plunged into the Huronian glaciation, beginning approximately 2.4 billion years ago and lasting perhaps 300 million years, potentially the most severe snowball Earth event in geological history. Temperatures dropped catastrophically. Ice may have reached the equator. The dominant biosphere, the anaerobic world that had ruled for over 1 billion years, was essentially annihilated. Not by an asteroid, not by a supervolcano. By the exhaled breath of organisms too small to see. The sulfur isotope record in marine sediments tells the story precisely. Around 2.3 to 2.4 billion years ago, the ratio of sulfur isotopes shifts in a way that only changes when the atmosphere crosses an oxygen threshold. This signal has been confirmed across rock samples from Canada, South Africa, and Finland. 3 separate continents, the same chemical moment, frozen in stone. The mainstream reading of all this is measured and rational. Evolution biologists frame the Great Oxidation Event as natural, inevitable, even necessary. Photosynthesis was a more efficient energy strategy. Organisms that could harvest sunlight outcompeted those that couldn't. The oxygen released was a byproduct, not a weapon, and the subsequent rise of aerobic life, the life that eventually produced every animal that has ever existed, including you, proves the crisis was a creative destruction. Oxygen didn't kill the world. It rebuilt it. But here is what that clean narrative quietly skips over. The cyanobacteria did not evolve a weapon. They evolved a behavior. And that behavior, at scale, rewrote the chemistry of an entire planet and erased the dominant form of life without a single act of predation, without a single collision, without any intention whatsoever. The most catastrophic near extinction in the 4 billion year history of life on Earth was an accident, a side effect. The deadliest creature that ever lived never knew it was killing anything at all. Some researchers ask whether that represents a template rather than a footnote. Human industrial activity has now altered atmospheric chemistry at a pace that makes the Great Oxidation event look gradual. We are not cyanobacteria. We are aware of what we are doing. But the cyanobacteria remind us that awareness has never been a requirement for planetary scale consequences. From the invisible and the ancient, we move to something you could almost see. Something with eyes. Compound eyes containing more lenses than any creature alive today, mounted on a body that science spent 100 years trying to make sense of. Anomalocaris. It is 520 million BCE, and nothing has ever needed to hide before. In the shallow tropical sea covering what will one day become the Canadian Rockies, the organisms of the Cambrian world drift and graze in a biosphere that has never known a predator worth fearing. There is no instinct yet for escape, no shell, no spine, no reflex that says run. And then something arrives with compound eyes the size of a human fist, a circular jaw that opens like a mechanical iris, and articulated claws designed for grip and precision. In a world where nothing has ever hunted, this animal is the first real nightmare. And its eyes are more sophisticated than those of almost anything alive today. The story of Anomalocaris is also the story of one of the longest cases of mistaken identity in the history of science. In 1892, its claws were described as a species of shrimp. Its mouth was catalogued separately as a jellyfish. Its body was classified as a sea cucumber. 3 different animals. All the same creature found in pieces, and the pieces were so strange that trained scientists could not conceive of them belonging to one organism. It was Harry Whittington at Cambridge, working with Simon Conway Morris through the 1970s and 80s, who finally assembled the Burgess Shale fragments into the single predator they actually represented. The Burgess Shale, buried in the mountains of British Columbia, is one of the most extraordinary fossil sites on Earth. The fine-grained mud of an ancient seafloor preserved soft tissue in detail that is almost never possible, and what it preserved of Anomalocaris was astonishing. Adults reached up to 1 meter in length, making this the largest animal alive during the Cambrian period. In a world measured in millimeters, 1 meter was monstrous. But it was the eyes that a 2011 study in Nature by John Patterson at the University of New England and colleagues identified from fossilized stalked specimens that stopped the scientific community cold. Up to 16,000 individual lenses, each one a facet of a compound eye capable of detecting motion across a wide visual field with the acuity of a modern robber fly. To put that in context, a dragonfly, one of the most visually acute hunters alive today, has around 30,000 lenses. Anomalocaris was already most of the way there, 520 million years ago, in a world that had never needed eyes like that before. The visual system did not arrive as a rough draft. It arrived fully engineered in the fossil record with no obvious intermediate forms in the layers below it. Its jaw was equally strange. 32 overlapping calcified plates arranged in a circular ring, opening inward like a camera iris to grip and crush prey. Bite traces matching the exact diameter and tooth spacing of that jaw have been found on enrolled trilobites from Canada to China to Greenland, confirming that Anomalocaris hunted across what were then separate ocean basins. It was not a local anomaly, it was a global predator. In 2014, Jacob Vinther at the University of Bristol and colleagues placed Anomalocaris within a stem group ancestral to all modern arthropods. Every insect, every spider, every crab, every millipede alive today carries a distant inheritance from this body plan. We are, in the loosest biological sense, its descendants, and yet it left no direct line. The jaw design, the claw architecture, the specific optics, all of it vanished. The mainstream explanation for the Cambrian explosion that Anomalocaris inhabited is an arms race. A newly diverse ecosystem produced a large, mobile, visually acute predator as an evolutionary inevitability. Its extinction at the close of the Cambrian is attributed to changing ocean chemistry and the rise of competitors with superior body plans. Evolution ran its experiment and then moved on. But the 16,000 lens eye is the part that resists that framing. An arms race explains why a predator emerged. It does not explain why the predator that emerged had optics that took evolution hundreds of millions of years to rebuild elsewhere. There are no clumsy prototype eyes in the Cambrian layers beneath Anomalocaris. The precision simply appears. Some researchers in evolutionary developmental biology ask whether the Cambrian explosion was not a gradual arms race at all, but something closer to a phase transition, a sudden system-wide reorganization of biological possibility. If so, Anomalocaris was not the cause of that reorganization. It may have been the first visible symptom of a change in the rules themselves. What changed 520 million years ago? And why did complexity accelerate so abruptly and then slow back down to the pace we consider normal? We may never have a clean answer, but there is a jaw design in the Burgess Shale that 32 plates of ancient calcite suggest was, for its moment, the most advanced engineering on Earth. From the Cambrian seas of Canada, we move forward 140 million years to a different ocean. Warmer, shallower, and ruled by something that didn't need 16,000 lenses to find you. It just needed its jaw open for 1/50th of a second. Dunkley osteus. Imagine a fish without teeth. Now imagine what replaces them. Two interlocking blades of exposed bone, the jawbones themselves sharpened by contact, each grinding pass honing both edges simultaneously, a self-maintaining cutting system that requires no replacement and dulls itself back to sharpness with every bite. The year is 380 million BCE. The inland sea covering what will one day become Ohio is warm, shallow, and dominated by armored fish. And at the top of that food web is something that doesn't bite so much as it operates. The jaw opens in 1/50th of a second. The suction it creates is strong enough to pull prey into the mouth before the prey's nervous system has registered that anything has moved. By the time you know it is hunting you, you are already inside it. This is Dunkleosteus terrelli, and the first fossil was described by J. Terrell in 1873 from Cleveland Shale specimens in Ohio. The genus was named for David Dunkel, a curator at the Cleveland Museum of Natural History. For over a century, the animal was understood primarily from its skull and thoracic shield, the only parts that calcified and preserved, and those parts alone were extraordinary. Adult skulls measured up to 1 meter across. Total body length is estimated at 8 to 9 meters. Weight approximately 3.6 metric tons. It was Philip Anderson and Mark Westneat, in a 2006 study published in the Journal of Experimental Biology, who finally calculated what that jaw could actually do. Using biomechanical modeling from the skull's joint geometry, they established a jaw closing speed of approximately 20 milliseconds and bite forces of around 4,400 newtons at the tip, rising to roughly 7,400 newtons at the bony projections equivalent to fangs. Those numbers are comparable to large crocodilians, but what separated Dunkleosteus from every crocodilian that ever lived was the mechanism. A 4-bar mechanical linkage system in the skull, unique in vertebrate evolution, that coupled jaw opening with cranial elevation, generating hydraulic suction as a simultaneous consequence of the strike. The prey was not just bitten. It was vacuumed into the mouth at the same moment the jaws opened. And then there is the self-sharpening blade. Teeth in every vertebrate lineage before and since are discrete structures, grown, used, and replaced. The Dunkleosteus jaw had none. The cutting edges were the bones themselves, maintained by the geometry of occlusal contact, kept sharp by the very act of closing. It is a passive maintenance system with no modern vertebrate equivalent anywhere in the 500 million year history of jawed fish. Fossilized regurgitation boluses found alongside Dunkleosteus skull material in Cleveland Shale, compacted masses of fish bones and scales indicate it swallowed prey in large pieces and expelled indigestible material, a feeding behavior more consistent with a shark than a bony fish. And Dunkleosteus belonged to neither of those lineages. It was a placoderm, a member of the armored jawed fish class that dominated vertebrate life for 70 million years before being erased completely. Erased in the late Devonian extinction, also called the Kellwasser and Hengenberg events, which eliminated approximately 75% of all species on Earth between 372 and 359 million years ago. Current research links part of that extinction to the explosive diversification of land plants whose deep root systems released nutrients into shallow coastal seas, triggering oxygen-depleting algal blooms that dismantled the reef ecosystems Dunkleosteus and its world depended on. The reefs died, the food web collapsed, and the entire placoderm class, not a species, not a genus, an entire vertebrate class, vanished from the history of life and never came back. The mainstream reading is clean. Dunkleosteus was a highly specialized apex predator, brilliantly adapted to conditions that no longer existed after the late Devonian collapse. It was too specialized for a changing world. Evolution moved on to other designs, but the self-sharpening bone blade is the detail that the specialization argument doesn't quite address. Teeth have evolved independently dozens of times across vertebrate lineages. Sharks reinvented them. Mammals reinvented them. Every time a vertebrate needed to cut, it grew teeth. The Dunkleosteus blade was never reinvented, not once in 350 million years of subsequent vertebrate evolution. If it was so effective, why did no descendant lineage, not even distantly, ever rediscover it? Some researchers in functional morphology ask whether there are solutions to biological engineering problems that evolution finds once and then, for reasons we don't fully understand, never finds again. The self-sharpening blade may have been one of them. An answer to the question of how to cut, so structurally specific to a now vanished body plan that the conditions required to reinvent it have simply never realigned. From the bone blades of the Devonian Ocean, we moved to dry land 345 million years ago, and to a body plan so large that it required a different atmosphere just to exist. Arthropleura. Picture a millipede. A real one, the kind you find under a rotting log, the kind that curls into a spiral when you touch it. Now make it 2.5 meters long, the length of a small car. Give it a body width of 50 centimeters. Now put it in a forest where the trees grow 40 meters tall, where the canopy is so dense that permanent twilight presses down through the fern fronds, and where the air itself, the simple act of breathing, is something your lungs could not survive. The year is somewhere between 345 and 299 million BCE. This is the Carboniferous, the age of giants, and the largest land invertebrate that has ever lived is threading between tree roots the size of pillars, pressing its body into the ancient mud, leaving tracks that will still be there 300 million years later for a geology student in Northumberland, England, to notice in the face of a freshly split boulder. That student found the animal in January of 2022, not by excavation, but by accident. A boulder had fallen from a cliff near Howick Bay and cracked open to reveal a slab containing the most complete Arthropleura specimen ever described. Neil Davies at the University of Cambridge and colleagues published the find in the Journal of the Geological Society. The specimen measured 75 centimeters wide. Total body length was estimated at 2.63 meters. Weight, approximately 50 kilograms. The largest land invertebrate in 475 million years of terrestrial animal life, confirmed not from ancient fragments, but from a rock that had been sitting on a beach until the sea decided to open it. For nearly 170 years before that discovery, Arthropleura was known only from isolated exoskeleton segments and trackways. Those trackways, called Diplechnites traces, wide parallel rows of footprints pressed into ancient mud, have been found in Scotland, Nova Scotia, and Germany. Some measure over 50 centimeters across. The animal was clearly real, clearly enormous, and clearly widespread. What we lacked was a body to go with the footprints. The body that Davies's specimen confirmed was only possible because of the Carboniferous atmosphere. Robert Berner at Yale, across decades of carbon and sulfur isotope modeling, estimated Carboniferous oxygen levels at 30 to 35%, compared to today's 21. Arthropleura breathed through a tracheal system, the same passive oxygen diffusion tubes that insects and millipedes use today. At 21% oxygen, tracheal respiration caps body size at a relatively modest scale. At 35%, the math changes entirely. The tubes can diffuse enough oxygen to sustain a body 50 kilograms in mass. The giant wasn't a mutation or an anomaly, it was a creature built precisely to the specifications of its atmosphere. Gut content analysis of one specimen revealed spores and plant material suggesting Arthropleura was a herbivore or detritivore feeding on the decaying organic matter blanketing the Carboniferous forest floor, which makes its size even more ecologically puzzling. 50 kilograms of passive leaf eater in a world with no large terrestrial predators yet capable of threatening it, in an atmosphere so oxygen-rich that any exposed flame would have ignited the landscape. The Carboniferous is named for the coal it left behind, the compressed and undecomposed remains of those 40-meter club mosses and tree ferns, which accumulated because the fungi that would eventually learn to digest lignin had not yet evolved. The forests were building a geological carbon battery. Arthropleura walked through the factory floor, and then the factory shut down. Approximately 307 million years ago, the Carboniferous rainforest collapse fragmented the vast equatorial coal forests as the climate became drier and more seasonal. The continuous canopy broke into isolated patches. Oxygen began dropping. The humid microhabitats Arthropleura depended on shrank and disappeared. It went extinct not with a predator standing over it, not with an asteroid incoming, but because the specific atmosphere that made its body possible slowly stopped existing. Paleontologists frame this cleanly. Arthropleura was a product of hyperoxic conditions. When the conditions ended, the animal ended. That is how ecological specialization works. Nothing about this is mysterious. But the Carboniferous rainforest collapse is itself a mass extinction event that almost nobody talks about. It does not appear in the standard list of the Big Five. It is not in most textbooks. A catastrophic collapse of an entire planetary biome, driven by climate change, that rewrote terrestrial life, sits largely unexamined in the popular imagination. And the coal that those forests left behind, the coal that Arthropleura spent millions of years walking over, is what drove the Industrial Revolution and is currently burning at a rate that is measurably altering the atmosphere's chemistry. The cyanobacteria changed the air and nearly ended the world. The Carboniferous forests built the fuel for the next experiment. Whether the arrow is pointing in a new direction is a question some researchers are asking with increasing urgency. From the coal forests of ancient Scotland, we cross 3 geological eras and an ocean to a desert in Peru, where a skull the size of a dining table was found embedded in rock that was once the seafloor of the most productive ocean in the history of the Miocene world. Leviathan Melville. It is 2008, and a team of paleontologists is working a fossil site in the Pisco Ica Desert of southern Peru, approximately 400 kilometers from the nearest coastline, in a landscape of sand and scrub that gives no indication it was ever anything other than desert. Then the excavation reveals a skull. 4 meters long, solid where a sperm whale's skull would be hollow, and lined upper jaw and lower jaw both, with the largest functional teeth of any predatory animal confirmed in the fossil record. Up to 36 centimeters in length, including the root. Crowns 12 centimeters exposed. This was not an echolocating whale searching the deep water for squid. This was something that found its prey by sight, by smell, and by the fact that it was large enough to hunt other whales and had the teeth to prove it. Olivier Lambert and colleagues published the formal description in Nature in 2010. The species name they chose was Melvillei, in honor of Herman Melville, who wrote Moby Dick. The genus name was Leviathan, from the Hebrew spelling of Leviathan, the biblical sea monster described in the Book of Job as a creature whose breath sets coals ablaze, an entity God invokes to illustrate the outer boundary of human comprehension. Lambert and his team felt nothing else in the fossil record deserved the name more. That is not a small statement from a group of professional paleontologists. The holotype skull, now housed at the Natural History Museum in Lima, estimates to a total body length of 13.5 to 17.5 meters, placing Leviathan in the same size class as a modern sperm whale. But the modern sperm whale has teeth only in its lower jaw. The upper jaw is smooth. Leviathan had interlocking functional teeth in both jaws, an arrangement that made the mouth a closing trap rather than a grasping hook. The skull also lacks the large spermaceti basin that living sperm whales use for biosonar, which means Leviathan navigated primarily by vision and passive hearing. It did not click to find its prey. It watched, and what it watched, based on the Pisco Formation's fossil assemblage, were baleen whales. Multiple species of baleen whale have been found in the same formation alongside the Leviathan skull, along with smaller toothed whales, seals, and sharks, including, in the same rock layers, teeth of Carcharicles megalodon, the largest predatory shark in history, which we will come to shortly. 2 of the largest apex predators that have ever lived, contemporaries in the same warm Peruvian sea, hunting the same prey in what paleontologists calmly describe as a highly productive Miocene ecosystem and what the rest of us might describe as the most terrifying ocean that has ever existed. The muscle attachment scars on the Leviathan skull's temporal region are proportionally larger than in modern sperm whales, indicating bite forces that no precise study has yet been able to calculate from incomplete material, but which scale estimates suggest substantially exceeded anything in the modern ocean. The teeth themselves are the physical evidence. 36 centimeters of tooth does not evolve to process small prey. The mainstream explanation for a Leviathan's extinction approximately 8 to 9 million years ago is the reorganization of Miocene ocean productivity. Cooling seas, shifting currents, the decline of the warm shallow water environments that sustained the large baleen whale populations it depended on. The macroraptorial sperm whale clade, of which Leviathan was the apex, was replaced by ancestors of modern killer whales, smaller and more ecologically flexible predators better suited to the new ocean. It was a specialist meeting the end of its specialization. But the simultaneity of Leviathan and Megalodon in the Pisco Sea is a detail that the clean extinction narrative tends to present without dwelling on. Two predators of that scale, same size class, same prey base, same ocean. No ecosystem before or since has produced that combination. Paleontologists acknowledge the coexistence. The full ecological mechanics of how that ocean sustained both of them at the same time remain, to put it gently, underexplored. Some researchers ask whether the Miocene ocean represents a productivity regime so far outside anything in the modern world that we are systematically underestimating what the deep past was capable of generating. The Pisco Formation alone has yielded more whale species than exist in the entire modern Pacific. The desert that holds their bones was once something the modern ocean cannot match, and we don't fully understand why. From the desert that was once the deadliest sea in the Miocene world, we turn back to the ocean, and further back in time, to the creature that outlasted nearly everything, that walked out of the sea before anything else tried, and that survived 4 separate attempts by the planet to end all complex life. Eurypteridae. You are wading in a shallow estuary, warm water, slightly brackish, clouded with suspended silt. Nothing has ever walked on land, no insect has ever flown, no lizard has ever basked on a rock. The land behind you is silent in a way that land has never been since, a silence not of emptiness, but of biological vacancy, a world of bare rock and thin microbial crust where nothing has yet figured out that the terrestrial surface is available. And then something moves beside you in the shallows. 2.5 meters of segmented armor, 6 pairs of limbs, compound eyes positioned on the top of the head to watch the surface, and a spiked tail. A scorpion. Larger than you, assessing the situation. The Eurypterids, commonly called sea scorpions, first appeared approximately 467 million years ago. That date comes from Pentacopterus decorahensis, a new species described by Yale paleontologists in 2015, which pushed the group's earliest confirmed appearance back to the Ordovician. They persisted until the end, Permian extinction approximately 252 million years ago. That is a continuous evolutionary lineage of roughly 215 million years, more than 40 times the total duration of the genus Homo. The largest confirmed Eurypterid is Jacalopterus rhenanii, described from a single fossilized claw fragment by Simon Brady, Marcus Poshman, and O. Eric Tetley in a 2008 paper in Biology Letters of the Royal Society. The claw alone measured 46 centimeters. Scaling from that measurement, total body length reached approximately 2.5 meters. Mass estimated at over 90 kilograms. This was the largest arthropod in the history of life on Earth. It lived in the early Devonian of what is now Germany, in water that was likely fresh or brackish, which is itself significant, because it means the Eurypterids had already moved from marine to freshwater environments, expanding their range in ways that positioned them to make the next step. Multiple Eurypterid genera show morphological evidence of terrestrial capability. Hibbertopterus and Campulocephalus had broad, flat bodies and robust short limbs, consistent with supporting weight against gravity, and trackway evidence found in Silurian tidal flat deposits in Ontario trace fossils called protychnites confirms that eurypterids crossed exposed surfaces. They were not the first land animals, but they appear to have been among the first predators to test the terrestrial environment, walking out onto a world that had no defense against anything coming from the water. And then the planet tried to kill them. 4 times. The late Ordovician extinction, approximately 443 million years ago, eliminated around 85% of marine species. The eurypterids survived and diversified into the vacated niches. The late Devonian event, 75% species loss, same result. The end Mississippian event, approximately 323 million years ago. Survived again. Each time, the eurypterid lineage rebuilt. Each time, it emerged into a less crowded world and expanded. The horseshoe crab, their closest living relative, has a fossil record extending to approximately 445 million years ago, with no significant morphological change, making it one of the most extreme examples of evolutionary stasis known. The design was so stable that hundreds of millions of years of natural selection produced no improvement worth implementing. And then the end Permian hit. 251.9 million years ago, confirmed by radiometric dating, triggered by the Siberian Traps volcanism releasing carbon into the atmosphere possibly over as little as 30,000 years. 96% of marine species, 70% of terrestrial species. The most severe mass extinction in the history of complex life. The eurypterids, having survived 4 previous extinction events spanning 150 million years of catastrophe, were gone. The mainstream explanation is straightforward. The end Permian's multi-stressor combination, ocean acidification, global anoxia, and temperature spikes occurring simultaneously and rapidly exceeded the adaptive range of even the most resilient lineages. Ecological flexibility couldn't compensate for the speed and breadth of the collapse. But 4 extinctions survived and then killed in the 5th is a data point worth sitting with. Some extinction researchers ask whether the end Permian's lethality lay not in any single stressor, but in the interaction effects between simultaneous stressors, a compounding toxicity that no prior extinction had produced. If so, the eurypterid story is not about an animal that finally met something stronger than itself. It is about a threshold that resilience, however extraordinary, cannot cross if the world breaks in enough places at once. From the animal that survived nearly everything, we turn to one that could not be correctly understood at all, even by the scientists holding its fossils in their hands. Hallucigenia. It is 508 million BCE on the Cambrian seafloor, and the organism moving through the sediment does not fit any category that will exist for another 500 million years. It has a worm-like body. 7 pairs of stiffened clawed legs on one side, 7 pairs of spines on the other. A head at one end, presumably, though this will be disputed. And somewhere inside, a throat lined with teeth that point inward toward the stomach, a second set lining the gut wall below, a design that ensures anything that enters the front of this animal does not come back out the way it arrived. Scientists found this creature and got it wrong for 38 years. Charles Walcott described the first Burgess Shale specimens in 1911 and classified the animal as a polychaete worm. Simon Conway Morris at Cambridge redescribed it in 1977 and gave it the name hallucigenia because the animal looked, in his direct words, like a hallucination. Conway Morris reconstructed it upside down, interpreting the legs as dorsal spines and the spines as walking tentacles. The reconstruction was published in a major journal, accepted by the field, and stood unchallenged for 14 years. Lars Ramskjöld and Ho Xiang Guang finally corrected the orientation in 1991 using better preserved specimens from the Chengjiang fossil beds in Yunnan Province, China. The animal had been inverted this entire time. Flipping it over revealed a creature that made considerably more sense structurally, though not by much. The head remained uncertain for another 24 years. It was Martin Smith at Cambridge and Jean-Bernard Caron at the Royal Ontario Museum who finally identified it in a 2015 paper in Nature, using scanning electron microscopy to examine the anterior end of Chengjiang specimens at a resolution that earlier tools couldn't achieve. What they found in the throat stopped them: a ring of radially arranged plate-like teeth pointing posteriorly toward the stomach, not outward, as in any predator designed to catch prey. Inward, toward the gut, in a configuration that would lock captured material inside the pharynx and prevent its exit. Below that, a second series of needle-like teeth lining the anterior gut wall. Two sequential sets of inward-pointing teeth in a feeding apparatus with no equivalent in any living animal phylum that has been described in the scientific literature. Phylogenetic analysis by Smith and Caron placed Hallucigenia within the Lobopodians, a Cambrian stem group ancestral to the modern phylum Onychophora, the velvet worms. This means that Hallucigenia, modern velvet worms, tardigrades, and every arthropod alive today, every insect, spider, crab, and millipede share a common ancestor somewhere in this body plan lineage. The inward-pointing teeth are therefore an evolutionary feature that was present in the ancestor of an enormous swath of modern animal diversity and then entirely abandoned somewhere in the 500 million years since. No living onychophoran has them. No living arthropod has them. The design was tried once, apparently worked well enough to build an apex-feeding organism around, and then vanished from the lineage without apparent trace. The mainstream interpretation is that Hallucigenia fed on sponges, organic films, and microbial mats in a Cambrian world where prey had not yet developed hard parts, and the inward teeth were an efficient solution to the problem of holding soft, slippery food items long enough to digest them. As the Cambrian world changed and prey diversified, other feeding strategies proved more versatile, and the inward-pointing throat design was eventually superseded. Evolutionary experimentation in body plan architecture. The Cambrian tried many designs, most were abandoned. But the 38-year error is not just an amusing historical footnote. It is evidence about the limits of expert inference from real physical data. 3 generations of trained paleontologists, working from actual fossils in hand, built a detailed and internally consistent picture of an animal that was completely wrong, and the error was not caught by better theory, but by better specimens from a different continent. If the orientation of a fossil can be reversed by the entire field for nearly 4 decades, how many other Cambrian organisms are still sitting in museum cabinets, reconstructed in a configuration that their actual anatomy does not support? Some researchers in Cambrian paleontology ask whether the Cambrian body plan explosion produced organisms inhabiting ecological and biomechanical spaces so unlike anything in the modern world that our tools of interpretation are simply not designed to handle them. The inward-pointing teeth of Hallucigenia suggest a prey capture environment so different from anything observable today that the design was not merely abandoned. It was made conceptually unreachable. From an animal that resisted understanding for over a century, we move forward 440 million years to the moment the ocean lost its master, not to another predator, but to the absence of light. Mosasaurs and the Chicxulub darkness. Every ocean on Earth, 66 million years ago, belongs to the same family of animals. Not sharks, not whales, which do not yet exist. Something else. Something with double-hinged jaws that allow prey items too large for a single bite to be repositioned and swallowed in stages. a second row of teeth mounted in the roof of the mouth on the pterygoid bones, a backup grip ensuring that nothing already caught can swim free, a paddle tail generating thrust like a shark's, a body reaching 17 meters from snout to tip in the largest adults. Mosasaurs. And they are everywhere, from the shallow chalk seas of what will become Kansas to the polar waters off what will become Antarctica, in every ocean on Earth, at every depth that sufficient prey can be found. They are the most geographically widespread marine apex predators in the history of vertebrate life. The type specimen, Mosasaurus hoffmanni, was formally described in 1829, though the bones had been known since 1764, when quarry workers uncovered a massive skull in the chalk mines near Maastricht in the Netherlands and had no framework to understand what they were looking at. Georges Cuvier would later identify it as a marine reptile, unlike anything alive. The largest mosasaur genera, Tylosaurus and Haenosaurus, are known from North American chalk deposits, with Tylosaurus bernardi specimens estimated at 14.9 to 17 meters total length. The skull in large adults exceeded 1.4 meters. Fossil mosasaur material has been recovered from every continent on Earth, including Antarctica, where Tanniwosaurus antarcticus was described from James Ross Island, confirming the group had adapted to cold polar seas in addition to warm tropical oceans. Stomach contents preserved in Cretaceous chalk tell the story of what they ate: fish, ammonites, smaller mosasaurs, indicating interspecific predation or cannibalism among juveniles. Diving birds. One specimen from South Dakota contains the remains of a Hesper ornithiform diving bird and a shark simultaneously, which is either an extraordinary accident of preservation or evidence of an animal consuming prey that had recently consumed something else. Mosasaurs evolved from varanoid lizards approximately 98 million years ago, the same lineage that produced modern Komodo dragons and monitor lizards, and diversified explosively after the ichthyosaurs declined and the plesiosaurs began to retreat, filling every vacant apex niche in the global ocean within roughly 15 million years. And then, 66.043 million years ago, confirmed by Rene and colleagues at the Berkeley Geochronology Center using argon isotope dating published in 2013, an object approximately 10 to 15 kilometers in diameter struck what is now the Yucatan Peninsula of Mexico, releasing energy estimated at 10 billion times the Hiroshima bomb. The immediate kill radius was continental in scale. But the continental kill radius did not end the mosasaurs. What ended them was what happened to the sky afterward. Johan Vellekoop at Utrecht University and colleagues in a 2016 paper in Geology analyzed fossil assemblages from Brazos River sections in Texas spanning the Cretaceous-Paleogene boundary and found evidence of a rapid collapse in marine primary productivity beginning within decades of the impact. Sulfur aerosols and combustion soot injected into the stratosphere reduced incoming sunlight to levels that shut down photosynthesis across the global ocean. The base of the marine food chain, the phytoplankton, the zooplankton that fed on them, the small fish that fed on those, all of it collapsed simultaneously, from the bottom up. The mosasaurs, at the top of a food pyramid that had suddenly stopped existing below them, found nothing to eat in an ocean that had quietly stopped working. Paleontologists are clear about the mechanism. The mosasaurs were large-bodied, high-metabolism predators with no physiological capacity for dormancy or sustained caloric restriction. A bottom-up food web collapse in a globally distributed apex predator is a straightforward extinction pathway. The impact caused the darkness caused the starvation caused the extinction. The chain is understood, but the specific framing, the asteroid as the killer, is almost universally how this extinction is described, and it glosses over the more unsettling reality. The mosasaurs were not killed by the impact. They were killed by the light going out and not coming back fast enough. The most powerful predators in the ocean did not lose a fight. They ran out of a world that had stopped producing food, and there was nothing their size, their speed, or their extraordinary anatomical sophistication could do about it. Some researchers in astrobiology note that any future scenario producing sustained marine photosynthetic collapse, whether from volcanic winter, atmospheric particulate loading, or other mechanisms, should be modeled primarily through apex predator starvation rather than direct mortality. The mosasaurs are the template for what that looks like from the top down. From the ocean that went dark, we moved to a sea that no longer exists, preserved in a desert that was once a shallow tropical world, and to a whale that kept its legs long after it had learned to rule the water. Basilosaurus. 150 kilometers southwest of Cairo, in the Egyptian Western Desert, the wind carves sandstone into shapes that have no business existing this far from water. There are no waves here, no salt spray, nothing that suggests the Sahara was ever anything but what it is now, a hyper-arid expanse where the ground is desiccated to depths of meters. And yet, projecting from the surface of the rock, emerging as the desert slowly erodes the layers above them, are the skeletons of whales. Dozens of them lying in their original swimming positions, as if the sea retreated so quickly that they simply settled into the mud and fossilized where they died. 18 meters long, serpentine spines, jaws full of serrated teeth. And at the rear of the body, where no modern whale has anything at all, 2 small hind legs. This is Wadi al-Hitan, the Valley of the Whales, designated a UNESCO World Heritage Site in 2005. The whales are Basilosaurus isis, and they are approximately 40 to 34 million years old, the fossilized remnants of a warm, shallow Eocene sea that the tectonic compression of the Nazca Plate has since lifted several hundred meters into the air and converted into desert. The seafloor where Basilosaurus hunted is now eroded sandstone in one of the driest environments on Earth, and the skeletons are emerging from it not as buried fossils requiring excavation, but as three-dimensional objects projecting into open air, as if the desert is slowly giving them back. Richard Harlan described the first specimens in 1834 and classified the animal as a reptile. The name means king lizard. Richard Owen corrected the classification to mammal in 1839. But the hind limbs were not confirmed until Philip Gingerich at the University of Michigan excavated Wadi al-Hitan specimens and described them in a landmark 1990 paper in Science. The femur alone measured approximately 53 centimeters. The tibia and fibula were reduced but present, 3 digits with phalanges. A structurally complete leg, too small to support the animal's weight on land, too small to function as a propulsive flipper, positioned behind the center of mass in a configuration that made it useless for swimming. Gingerich proposed that the legs served as grasping organs during mating, a copulatory guide in an 18-meter predator navigating reproduction in an open ocean with no stable substrate to brace against. Basilosaurus isis reached estimated lengths of 18 to 20 meters, longer than a modern sperm whale, with a highly elongated serpentine body plan and a vertebral count higher than any living cetacean, producing the eel-like flexibility visible in reconstructions. Unlike modern toothed whales, it lacked the melon, the fatty forehead organ used for biosonar. Basilosaurus could not echolocate. It hunted by vision and passive hearing, closer in sensory strategy to a large shark than to any living whale. And it hunted other cetaceans. Multiple specimens of Dorudon atrox, a smaller contemporary roughly 5 meters long, found at the same Wadi al-Hitan site, show skull puncture wounds matching Basilosaurus tooth spacing, direct physical evidence that the first great whale was an apex predator that ate other whales, a behavioral strategy that Leviathan would independently rediscover 27 million years later in the Miocene Pacific. The Eocene-Oligocene transition, approximately 33.9 million years ago, brought a dramatic global cooling event associated with the opening of the Drake Passage between South America and Antarctica. Ocean circulation reorganized. The Tethys Sea closed. The warm, shallow water environments Basilosaurus depended on became cold, deep ocean, and the echolocating, streamlined, deep-diving whale body plans that replaced it were better suited to the new world. Basilosaurus did not survive the transition. The evolutionary interpretation is uncontroversial. Basilosaurus is a transitional form in cetacean evolution, not a missing link, but a clear intermediate between the four-legged land mammals that entered the sea 50 million years ago and the fully aquatic whales of today. The retained hind limbs are vestigial structures preserved because they served a reproductive function, eliminating the natural selection pressure that would otherwise have removed them. Its extinction reflects the closure of the Eocene warm water ecosystems it was built for. But the image that the physical evidence produces is stranger than the word transitional suggests. Basilosaurus was not struggling toward becoming something else. It was an 18-meter apex predator at the peak of its ecological power, ruling an ocean that no longer exists, in a sea that is now a desert, keeping legs it had found a new use for, in a body that had fully committed to the water while retaining the anatomical memory of the land. It was not between two worlds. It occupied its world completely. The legs were not a remnant of failure. They were a retained tool in an animal that had no reason to surrender anything that still worked. Some researchers ask what the retention of functional hind limbs in the most powerful predator of the Eocene ocean tells us about how evolution actually operates at the system level. Vestigiality is usually framed as the slow disappearance of structures no longer needed. Basilosaurus suggests something slightly different, that evolution is less interested in tidying up the past than the standard narrative implies, and that structures built for one purpose can persist indefinitely if they find another use, however different from the original. The legs that walked onto land 40 million years before Basilosaurus was born were still there in the most formidable ocean predator of the Eocene, repurposed, reduced, but present. Evolution, apparently, does not throw things away until it absolutely has to. From the whale with legs in the desert sea, we arrive at the last animal on this list, and perhaps the most famous. The one with the 18-centimeter tooth. The one that ruled the warm ocean for 20 million years and was not defeated by anything it could bite. Megalodon. An 18-centimeter tooth. That is what most people know about Megalodon. The tooth in the museum case, the serrated edge, the weight of it in the palm. And the tooth is extraordinary. Louis Agassiz gave the species its formal scientific description in 1843. Medieval Europeans who found the teeth in coastal cliffs called them tongue stones, the petrified tongues of dragons or giant serpents, which is not the worst inference available to someone with no framework for geological time. But the tooth does not tell you the most important thing about this animal. The nursery does. In the Gatun Formation of Panama, buried in sediment that was once a warm, shallow coastal lagoon in the Miocene epoch, Catalina Pimiento and colleagues at the Florida Museum of Natural History identified a megalodon nursery ground in a 2010 paper in PLOS 1. The evidence was in the tooth size distribution. 87% of the teeth recovered from the formation were consistent with individuals under 10 meters. Juveniles concentrated in a shallow, warm water coastal environment that matched nursery habitats used by modern sharks for pup protection. Megalodon did not just patrol the open ocean. It organized its reproduction around specific coastal geography, returning to the same shallow, warm water locations across millions of years with enough consistency that we can identify individual nurseries in the fossil record today. This is behavioral investment. This is ecological commitment at a scale that the single large tooth in a display case does not convey. Using body scaling models derived from great white shark jaw mechanics, Stephen Rowe and colleagues estimated Megalodon's bite force at somewhere between 108,000 and 182,000 newtons in a 2008 Journal of Zoology study, approximately the highest estimated bite force of any organism in Earth's history. Maximum body length estimates using scaling relationships between tooth height and total body length established by Gottfried and colleagues in 1996 place the largest individuals at 15 to 18 meters. Total body mass in adult specimens at the upper end of that range would have been in the range of 50 to 70 tons. Fossil whale bones with megalodon bite marks have been recovered from Miocene and Pliocene deposits in North Carolina, Virginia, and Peru. The bite patterns show preferential targeting of flippers and tail flukes, a disabling strategy consistent with hunting prey larger than the predator itself. And in the same Pisco Formation of Peru where Livyatan melvillei was found, megalodon teeth occur in the same rock layers. Two apex predators of equivalent size class, both hunting large baleen whales, contemporaries in the same Miocene Sea, for reasons that the Pisco Formation documents in the fossil record and that paleontologists acknowledge without fully explaining. Pimiento and Balk, in a 2015 PLOS-1 study analyzing a global database of megalodon occurrences, found that the distribution contracted significantly in the Pliocene before full extinction, with a pronounced loss of low-latitude shallow water occurrences. The extinction date was refined to approximately 3.6 million years ago. The timing coincides with the closure of the Central American Seaway, the gap between North and South America, whose closure was completed approximately 3 to 3.5 million years ago, reorganizing global thermohaline circulation, cooling tropical seas, and eliminating the shallow warm water coastal environments that megalodon depended on for its nursery grounds. The great white shark, long proposed as megalodon's evolutionary descendant, is now understood through genetic and morphological analysis to have diverged from a separate mako shark lineage approximately 4 million years ago. Great whites and megalodon were contemporaries, not parent and offspring. The competitive displacement of the largest predatory fish in history by a smaller, colder water, more ecologically flexible predator represents one of the clearest examples of competitive exclusion at apex predator level that the fossil record contains. The mainstream explanation is comprehensive: cooling ocean temperatures, closure of the Central American Seaway, reorganized prey distribution, declining shallow warm water habitat for nurseries, and competitive pressure from the rising great white lineage. Megalodon was a specialist. Its specific conditions disappeared. It disappeared with them. But the nursery ground data introduces a dimension that the standard narrative of specialist meets changed conditions tends to pass over. Megalodon had survived numerous climate shifts across 20 million years of evolutionary history. Its populations had contracted and expanded before. What was different about the Pliocene was not the magnitude of environmental change, but its specific character, the simultaneous loss of the warm, shallow coastal geography required for reproduction, combined with the arrival of a competitor better suited to the new ocean. The teeth were not the vulnerability. The nurseries were. An animal that had ruled the warm ocean for 20 million years with the most powerful bite in the history of life was undone not by anything that challenged it directly, but by the quiet disappearance of the specific coastal shallow water it needed for its young. That, in the end, is perhaps the most unsettling thing about Megalodon's extinction. Not that it was defeated, but that it wasn't. The ocean changed its geometry. The nurseries vanished. And an animal that nothing alive could challenge simply ran out of a world calibrated to its requirements. 10 creatures, 2.5 billion years of deep time, from the first photosynthetic microbe to the last megalodon nursery. And across all of them, the same pattern keeps surfacing in ways that the standard narrative of slow, orderly, progressive evolution does not quite contain. None of these animals died easily. The cyanobacteria did not die at all. They won, and the winning nearly poisoned everything else. Anomalocaris arrived with precision optics that evolution has not fully rebuilt in 500 million years. Dunkleosteus engineered a jaw mechanism that no subsequent vertebrate has rediscovered across 350 million years of opportunity. Arthropleura needed a planet with a different atmosphere just to exist. Leviathan and Megalodon shared the same Miocene sea, two of the largest apex predators in history competing in the same water. In a productivity regime, the modern ocean cannot match. The Eurypterids survived 4 mass extinctions before the 5th found a way. Hallucigenia was reconstructed upside down and backwards by professionals working from real specimens for 38 years. The mosasaurs were starved by darkness, not killed by fire. Basilosaurus ruled a sea that is now a desert and kept its legs for a purpose its ancestors never intended. And Megalodon was outmaneuvered by geography, not defeated by any predator it could have faced. The mainstream explanation for each of these is coherent and, in most cases, well supported by evidence. Evolution optimizes for conditions. Conditions change, specialists die, generalists survive. The fossil record is a graveyard of solutions that worked brilliantly until the problem they were solving changed. That reading is not wrong. But what these 10 creatures collectively demonstrate, taken together rather than individually, is something slightly different. It is not the fragility of specialization. It is the fragility of conditions. Every one of these animals was not killed by something it couldn't fight. It was killed by a change in the rules it was built for. Atmospheric chemistry, ocean temperature, a closing seaway, a dimming sky, the specific coastal geography required for reproduction. The rules that made these bodies possible simply stopped applying. That should make us think carefully about our own conditions, our cities, our food systems, our atmospheric chemistry, our ocean circulation. All of it is calibrated to a specific set of planetary parameters that the fossil record shows are not permanent. The cyanobacteria did not intend to nearly end all life. They were simply very good at what they did, at scale, until the chemistry changed. The coal that Arthropleura walked over for millions of years is what powered the Industrial Revolution. The warm, shallow seas that Megalodon depended on for its nurseries cooled, and the nurseries disappeared. The patterns are available to anyone willing to look at them directly. Most people walk through a natural history museum, see the big tooth in the case, and move on. They take the label at face value, but you made it here, which means you looked past the tooth and asked what killed the animal behind it. That is not a trivial distinction. It is the difference between consuming information and actually thinking with it. This channel exists for the second kind of person. Stay here, keep watching, hit subscribe, and drop your answer in the comments below. Which of these 10 extinctions do you think has the clearest warning for us today? Not the most dramatic, not the most famous, the most instructive. Build your case. Let's see who's paying attention. These animals were not myths. They were not monsters invented to frighten children. They were real, and the planet produced them, sustained them, and then ended them, not out of malice, not out of design, but because conditions changed and the rules they were built for stopped applying. The cyanobacteria that started this list are still here. They are in every ocean on Earth right now, still exhaling oxygen, still doing what they have always done. The conditions they created are the conditions we breathe. What we build our world inside of, what we assume will always be there, is never as permanent as the fossil record makes it look. The 10 creatures on this list were the most formidable things alive in their moment, and their moment ended. The tooth in the museum case is not a trophy, it is a reminder. The largest predator in the history of the ocean left behind a tooth and a nursery in a desert, and the nursery tells you more than the tooth ever could.